Any questions from last time? So, let me give you this last theorem that I wrote down, but we haven't proved yet. But I be a finitely generated field. Then I is invertible if and only if I is locally principal. I put that other condition in here as well. Okay, so I'm going to do the equivalence 1 and 2. Oh, and by the way, last time we showed that this hypothesis I finitely generated is necessary because we built a strange domain where you had an ideal that was not finitely generated, but was locally principal for all maximal ideals. So suppose first that I is invertible. Oh. Yes. One of those be should the third one be special? Right, absolutely. Yes. Suppose I is invertible. The fact that this is locally principal is not too difficult. So, no. This is always the case, right? This is actually easy to verify. Both these containment trees did verify. For all multiple sets. So in particular, so IM is invertible, right? In particular, IM is invertible ideal of RM, where here M is, of course, the multiplicative set that is R complement the maximal ideal. So, what do we have? We have that IM is invertible, and then RM is local. Well, quasi-local. So IM is because, as you probably recall from last time, we proved that if you have any invertible ideal over a quasi-local ring, it's always principal. Okay, so this depends on the previous result. It's not too bad. 2 implies 1. This is the interesting part. So here, by the way, let me point out that of course 1 implies 2 does not imply or does not require the hypothesis finitely generated. Right. So if it's invertible, it doesn't require the hypothesis because invertible's already finally generated, right? So that condition was kind of forced in from there. For the other direction, let's suppose that suppose this is finally generated and so there, right? I am principal. All minus five. So what we want to do is we're going to go for a computation here. Assume that I inverse, of course, we know that I inverse is always contained in R. Let's suppose that this is actually strict, right? So what does that mean? Well, it means that I inverse, since it is strictly contained in R, must be contained inside some maximal ideal of R. And so what are we going to do with that? Well, we're going to focus on the generators here. So let Y be the generator of IM, right? And of course, I can do this because I'm assuming that every I localized to M is principal. So it's got some principal generator Y. Now, for each Xi, that is, for each one of these generators of I here, I can find something in S such that SI, XI is in the ideal of Y. Right? Because really what this is saying is Xi is in R and Yi, well, Yi over Si. Well, actually up to something in S. And of course, we can choose our generators so that, yeah, and in fact, what I'm going to do here is, I didn't say it, but let's assume that I is in fact ideal R, right? And if it's not, I'll just multiply it by something to bring back in there. So really what we're saying is each Xi times something in S include the denominator in the B and Y, because in the local ring here in IM, each SI, XI must be an I, so this must be in the ideal generator by Y in IM. And so let's build yeah. But S be the product of all these SIs that we need, right? And notice I only need K of these, and this makes sense because of the fact that I is finite generated. And it's this point right here that it hinges on. We lose things. The ideal I is not finitely generated. Note S Y inverse conducts each xi into R. Just looking at this equation here, because for example, SI conducts Y inverse, I'm sorry, SI inverse conducts XI into R. And so in particular, this longer string of elements of R will conduct each XI into R. And so the magic of that is that so SY inverse is NI inverse because it conducts every generator of I back into R. And so SY inverse times Y is equal to F, which is in I inverse times I, which is contained in M. So S is in M, which is a constant. So that's kind of interesting. So that kind of covers it. Let me ask you this though. What about the third condition? One is invertible. Two, isometric principle. Three, IP principle. And I said I kind of threw this last one in just for fun. Can anybody explain? Well, okay, how about this? That was the easier one, right? Because if I localize a P as principal for every P prime ideal, then it's certainly true for every maximal ideal, right? So this is true for every maximal ideal. So if the statement is true for every prime ideal, then it's true for every maximal ideal. Why is the other way true? By explain why that's true. Suppose see, now this is a little bit more befuddling, right? Because there's more primes than maximal ideals, probably, right? And, every prime ideal is contained in the maximal ideal, right? I mean, maybe it is itself, right? How does this help? Let me ask you this. What's the relationship between those two?
Does the inclusion just reverse?
It does, right? I mean, here's kind of a sloppy way to think about it, but I think it holds water. P is the smaller one, right? When you localize it here, you're turning everything outside of P into units. Here, you're only turning everything outside of M into units, right? This thing has more units, right? It's closer to the quotient field. So this is the big one, right? So if IM is principal here, it has to be principal up here, right? Because when you lift this ideal up to this bigger ring, right, the generator here will certainly still generate out of here, right? In fact, in the extreme case, just take P to be zero ideal, right? And now that principal generator just turns into a unit. So I think that's worth noting here that actually the localizations, when you take R localized to P, you actually get something bigger because you've got a smaller prime. So the complement of the smaller prime is a bigger number of things that you can turn into units. Okay. Any questions? Questions? Okay. So now we're going to talk about Nostellensites and polynomials. One might argue that the Hilbert Nostellensites is like a big major kind of player in algebraic geometry. It's very important there. We're going to go with a very algebraic approach. At first, you're going to think that I've had a stroke, right? Because I'm going to start talking about these P domains and so forth. It all lost its mind. But don't worry, it will come full circle, and we're going to get to the connection with the Hilbert Nostellensites and polynomials as an application of all this. Okay. Theorem 431. And I want you to think about this, because I think this theorem here, this is a great example of this. So I want to write this theorem up here. Let R be a domain of quotient. And let U be an element of right. Following conditions are equivalent. Number one, R is finitely generated as a ring over R, or K is finite condition. And two, okay. Let me prove this before I ask a rather probing question. So the content of this theorem says the following. If you have a ring R, if you have a domain R with quotient OK, let's suppose, just for a moment, that you can find that the field is finitely generated as a ring over R, right? By the way, for my prototype of rings is always the integers, right? And this is certainly not true for the integers, right? I agree with that. Because if you have finitely many generators, right, let's say that they're rational numbers, then if you look at all the denominators, there's only finitely many primes involved. So no matter what you do, there's always going to be some stuff left over if you only use finitely many. But let's suppose that K is finitely generated as a ring over R, then K is actually equal to RU for a single element. So what this says is If you can generate it finitely, you can generate it with a single element. That's what this is. Proof. I hate being the Mac guy that writes that, but I think this one is pretty clear, right? Because by definition, K is finitely generated by one element, right? The interesting part is the fact that if you have finite some n generators, then you can do it at one. So now suppose then certainly right. Because, for example, notice that when you join 1/c, you get each of these, right? For example, you get A1/B1, just multiply in the numerator by all of these B's and then an A1, right? And so forth. So if you got this, then if K is this, then K is certainly got by that one element, right? Okay. Here's my. Okay, so there's two things to sort through here, stupid and vacuous, right? These conditions, there certainly must exist. Somebody give me the smart aleck situation where R is a domain with quotient field that satisfies one of these conditions. Somebody give me an example of a domain whose quotient field is generated over it by finding any elements. The field itself, right? That's the non-vacuous one, right? So we've got over that hurdle. Certainly a field itself will work. Okay, now stupid, right? Is there any example that's not a field? Right? Because obviously the integers fail, right? Think of such an example. It might be valuable. Actually, let me think about that. Yeah, so a lot of valuation domains this will work for. You've got it. I think you might need to have a height 1' that could work. But so many valuation domains. So here's an example. Look at formal power series over a field. One variable. There is only one prime element in this. This is the principal ideal domain of only one prime, only one non-zero prime, namely X. If you turn X into a unit, you get the quotient field. So notice that F power X going 1/X is a field. And of course, that's the quotient field because X is in the domain. Right? Let me kind of draw you a picture of this. In fact, this sort of thing will work for any one-dimensional valuation domain generated by X. There's 0 in here. If you have a one-dimensional valuation domain, it looks like this, right? Now, just take any overlay. We'll call this B, let P. And what do we know about an overring of an evaluation domain? It is a valuation domain, that's right, and it's also It's a localization. So P must be VM or V0. It has to be a localization of one of those two primes, right? But this one is P. And this one is the quotient field. That means if you take any element of V that is not in the maximal ideal and adjoin it, you have to get the whole quotient field. Because if it's no longer T, right, if it's no longer T, it's got no choice but to wiggle all the way up to the quotient field. Are you okay with that? Yeah. Something disturbing.
I'm just looking at the. So T is an overrange, so T is one of those,
Uh-huh.
and then you have V that is T.
Oh, right, because if you localize at the original maximal ideal, then what you're doing is you're turning all the stuff outside the maximal ideal into units, but they were already units in the first place, so you haven't really gone anywhere. Right, since this is evaluation, like, so if you look at, if you look at this V localized at M, what you're doing is you're allowing everything outside of the maximal ideal to be in a denominator, but it already was, because it's a unit.
So V is T. That's, okay.
DM is, what's it now? Oh, yeah, yeah. I didn't even see it myself. That's what I meant to say. Thank you. Yeah. Let me ask you this, what if I had another picture like this? What if I had a two-dimensional evaluation domain? Yeah, well, evaluation domains, because you order their ideals linearly like this. What if I have one that looks like this? All right, overrings, I'll call it V. Right. So what happens if you localize? So what happens if you localize at 0? You're turning everything outside of 0 and you get the quotient. If you turn everything outside of M into a unit, you're at the same place, right? What happens if you localize here? Well, what happens is now you turn everything outside of P into a unit, and so now you're back down to this case too, right? So what do you have to do to get the quotient field? Basically, all you have to do is invert any non-zero element in here, right? That is, if you take V, adjoined with 1 over X, right? So basically what I've done is I've put S in a multiplicative set. When you localize here, or when you adjoin 1 over X, because again, it has to be a localization, right? Because all overrange evaluation domains are localization. What happens is, in this ring here, everything dies. That is, everything turns into a unit. Every prime ideal is killed that intersects this set. Well, notice P intersects this set, and so does M because it contains P. The only thing that doesn't intersect is a 0 ideal. So when you adjoin this, you will have a valuation domain that has only the 0 ideal, right? And so it'll be a quotient field. So this is another example. So if you take any element that's two-dimensional valuation domain and you adjoin something that's in this height 1 prime ideal, this kills that prime ideal and everything above it, leaving only the 0 ideal. So valuation domains appear to be a rich source. And in fact, since the ideals are linearly ordered, really what we need to have is a height 1 prime, right, to do this, right? Because if you have a height 1 prime, that is a small prime that's not 0, if you kill anything in here, it kills this prime, or if you invert anything in here, it kills this prime and all primes above it, leaving only zero out there. So the only way that I can't figure out how to do this is if you have a valuation domain that has no background prime, and you can actually build these things, which no matter how small prime is, you get something a little bit smaller. So these things actually exist. Is there one that's not a valuation domain? Well, yes, I can really kind of do that. So here's one that's not a valuation domain. This is a big fat sheet, but I'm gonna do it and let it ride. This is power series in the variable X over a field, but I'm missing the linear term. Again, if I take one over, well, actually 1 over X squared will do. This gives me the total field. The only thing that made me, notice that, when I take 1 over X times X cubed, I get an X. So now I've got an X in this thing, right? But, now that I've got X in here and I've got 1 over X squared, now I've got 1 over X. So there you go. Am I okay with that? But why is the original ring? Why is this original ring not a valuation domain? I cheated really to make a rip-off example. It's not even integrally close, right? Because notice that X is in the quotient field of this thing, and X squared is in that ring, but X itself is not in there. This can't possibly be a valuation domain. And in fact, for more direct verification of that, take the 2 elements in here, X squared and X cubed. Neither one of them divides the other. X squared didn't divide X cubed because there is no X, right? So it's not a valuation. Okay. Right, theorem. Let's let R be a domain with quotient field K. And that U be a non-zero element of K. Oh no, R. One. Any, equivalent. Any non-zero prime ideal of R between U any non-zero ideal of R contains a counter view. Ideal, right? U and 3 A is R joined with U inverse. Okay, so this, and of course you can see this weaving its way through the examples that we just did, because here's some conditions on it. Following are equivalent. Any non-zero prime contains U. Any non-zero ideal of R contains a power of U. And finally, K is R joined with U inverse. So let's go through this. Okay, so we're under the assumption that any non-zero prime ideal of R contains U. We want to show that any non-zero ideal of I contains power. So well, Well, that'd be a non-zero ideal of R. We want to show a power of units in that, right? Well, consider. Well, actually, what are you supposed to consider? It would be a real radical move on our part. Yeah. Yes, let's consider this. Consider radical I, which is a set of X and R, X, N, I, so N. Now, that's kind of not good enough unless you remember something very important about the radical. And what is that? Does anybody remember characterization of the radical? Okay, it's the intersection of all primes that contain it, right? So radical I is the intersection so a radical I is the intersection of all primes that contain I. But what do we know about all the primes? Well, we know that U is contained in every last one of these primes. Since U is in V, we're all P and R, U must be in the radical I. And therefore, U N is an I. Yes.
We also argue for one was to assume there's an ideal that contains no power of U, then all the powers of U form multiple of the closed set, and we can expand I to an ideal which is maximal with respect to that set, and that's gonna be prime.
That's right. And I guarantee that'll work because that's basically the proof of why that thing works. So yeah, that'll work. Let's see, how about 2 implies 3? So I know that every non-zero ideal of R contains a power of U. So suppose so here, my basic strategy is this. I'm going to pick an arbitrary non-zero element of R, and I'm going to show that its reciprocal actually lives in R adjoined with U inverse, right? That's basically my strategy. So if I can show that really what I'm showing is any element of R becomes a unit and R adjoined with U inverse. And so that means that R adjoined with U inverse must be quotient. So this ideal contains a power of U. So U to N DR. So R. Right. So So the reciprocal of V, which is R over UN, is in R adjoint U. Hence, V is a unit. R UN. Since each element of R is a unit, well, non-zero. Since each non-zero element of R is a unit in R U inverse, the quotient field K of R is contained. and R U inverse. So we have that K and clearly we have the other component. This must be true because of course R is contained in its quotient field and U is an element of R, and so it's U inverse is contained in the quotient field, so this is all contained here as well. So finally, we need 3 implies 1. So in this case, what we want to do is show that U is an every prime ideal. So suppose K is R U inverse. And suppose P inside R is a prime ideal. And this actually sort of mimics what you were saying earlier, Jared. If U is not infinity, so of course I hope the U is infinity, but if it's not, then 1 U squared U forever and ever is a multiplication from both set such that P intersect S is empty. So P must survive. Or going U inverse is K, and this is a contradiction. Because no non-zero, and I should have said that, is a non-zero prime ideal. No non-zero prime ideal survives in a field. Okay, any questions on that? I kind of skipped over this. Oh, yes. Recall such a domain what I may notice where K is equal to R U, so U in K, a G domain. So one of these domains that satisfies these conditions is called a G domain. So here's kind of the first theorem. And like I said, in our quest for the Bell-Stellan sites, when we come at it, these G domains are actually going to be useful because they're going to tell us a lot about polynomials in particular. So 4, 3, 3. Let R be a G domain, the quotient field K. And suppose that T is an overring of R. What do you suppose my conclusion about T is? The T is also a G domain. I skipped the proof of this, but this is almost immediate, right? Because R is a G domain. The quotient field is R adjoined with U, right? And R adjoined with U is contained in T adjoined with U. It's also going to be K. Right? Because adjoining U to little r makes it grow to the quotient field. Adjoining to the bigger T certainly makes it grow to the quotient field as well. And of course, what's important also is that both T and U are also inside of K, so you get the other containment we need. On the other hand, there's kind of contrasting proposition. The domain Rx is never a G domain. If R is a domain, what else? Never. There is a way to tackle this. There's a clever way to reduce this problem. Rx, very bad, can be. It can be incredibly bad. But let's revisit. Did you see how easy this proof was? It always amazes me when theorems that have easy proofs have nice applications. Trying to figure out whether this is a G domain. Can I add something to this that makes the quotient field? It's not so clear. However, I can use this. If Rs is a G domain, so is Kx. Okay, it's a quotient field. Right? Because Kx is an overlay, right? I mean, remember, what's the quotient field of R square brackets X? It's rational functions in over K, right? Because the quotient field of Rx will certainly contain the quotient field of K, so it'll contain K square bracket X, and then in fact, the quotient field will be the rational functions of over the field K, right? So this actually is a massive step forward because, I mean, that can be awful, right? Rx can be just terrible, all kinds of terrible things can happen in Rx. However, Kx is much easier. No matter what K is, this is a PID. So that's going to be the cliffhanger, right? So that's like Game of Thrones in season 7 or something. And we'll come back to this next time. We've reduced this down to a much easier thing. This is often a really cool thing to think about. Any questions? Okay, if you got my email today, I will be available from 11 to 2 today. So if you were planning to see me, come give me a holler now, and I can either help you now or we can get it fixed up for you later. So, all right, other than that, I'll see you guys on Wednesday.